Okay, just a quick poll. How many people have actually seen one of these broadcast in real life? Wow. Okay. I I thought it was just me. So that's just in case I wanted to run out of here, but I think I'm going to carry on. So this talk is about getting Ruby to speak to Python with a Lisp, with a bit of Lisp. And I'm really excited to be here because I have given this talk at a Ruby conference, or 2 Ruby conferences, and a colleague of mine has given it at a Python conference, but it always kind of felt a little bit subversive. People were kind of like, oh, what are you doing? Bringing this other thing. And so I don't have to worry about that at all here, and I can actually dive into a lot more detail. So before that, who am I? I'm not internet famous. Actually, maybe I am, because I've done Julia. I've saved the world 8 times, but it only took me 8 days, so it was fine. And I'm also just polycurious. And I'm basically the technical guy at a company called Intellection. We started up in 2010, and like many startups in 2010, we started with Ruby on Rails. We had a lot of boilerplate stuff we needed to get out. We needed to iterate very quickly, releasing every few weeks with trying to basically sell what we've already sold, or deliver what we've already sold. So Rails was great for that. It allowed us to spend a lot more time on the domain, which turned out to be quite important because we didn't actually know the domain. We work with market research data, and it turned out there was quite a lot more to it than we thought. We didn't have a there was a requirement inside a large company, so we knew what we wanted to deliver, but we needed to spend a lot of time actually becoming experts in that. So by 2012, we knew the domain quite a lot more. We kind of realized that data science is a thing. The whole web framework was pretty mature. We didn't really have to worry about that anymore, but working with the data was becoming a real pain in the ass. And it was getting really hard to keep it going faster, working on better data sets, and keeping agile. We were really slowing down quite a lot. And if you're using Ruby and iterating slowly as well, then what the hell are you doing? And just so I don't offend the Rubyists in here, I am a Ruby guy. I do like Ruby a lot. There are tens of gems for everything except working with data. So we did try, though. This is a very scientifically accurate chart. It's a roughly straight line on a log scale. And we did try and improve the performance in Ruby. We used a lot of different things. We kind of succeeded. But behind the scenes, there was a different story. We started to sacrifice abstraction power and started to increase complexity. And I really view any product as having a complexity budget, and we were just eating it with performance requirements. And that's largely because when you start attacking hotspots in a dynamic language by going down in specific cases, you aren't really creating a coherent layer upon which you build in. You're just digging holes in a high-level system. So it started to worry me that I know what happened to this guy. The guy who was in charge of Twitter tech, who wanted to carry on doing it in Ruby. So I thought, okay, it's time to admit that Ruby might be lacking in numerical performance. I need to start thinking of a polyglot solution. We need something with much more numerical performance, better features, better abstraction. It was all feeling very, very hacky. So 2013, spoiler alert, Python was identified as a good fit. I was pretty surprised, because I thought, cool, I'm going to be learning Haskell, I'm going to be doing Clojure or something, but we needed to go onto a framework that was a really good fit for us, and there's a particular type of data that we work with, and Python is very well suited to that. And the whole stack is very, very deep. And what I've got here is really a list of technologies that are relevant to us. And everything on the right-hand side relies on the thing to the left. And the thing to the left took years to get mature. So if you want to replace that in any language, you have 6 years, I think, to try and maybe some of the higher order languages that compile down, you maybe cut a year or two off that. But it's a difficult stack to dislodge. So don't really have a huge amount of time to go into depth about any of these things. I'm going to briefly talk about Numpy for those of you that don't know. It's not super sexy. It's just array computing, and that basically provides vectorized operations for Python, which turns it from a very slow language for dealing with numbers to a pretty fast language for dealing with numbers. And it's the bedrock upon which the rest of scientific Python is built. Quick question. Am I speaking too quickly? Okay, good. I just need to talk about vectorization because I think it is relevant, particularly in this conference. People have talked about dynamic languages and the performance and statically typed languages. Vectorization is basically it's an abstraction where let me just put this another way. One of the performance problems that you have with a dynamic language when you want to say just add an array of floats to add every element together to get the total. It's very simple to do in Ruby. You can just go array reduce with a plus and you'll get your answer. There is a sum method in Ruby as well. That's kind of vectorization. But it is very, very slow to do that because Ruby does not know that it's an array of floats. So it has to check every single element. Are you a float? It has to check, am I going to overflow? Ruby doesn't overflow. It type widens. So if it's going to be above 2 million, billion, whatever, it needs to switch to a big int. Monkey patching, it needs to check every single object, whether someone might have added a method to it and redefined addition. All that stuff is just more opcodes where C is doing 3. I'll probably be proven wrong in the Julia talk, but it's probably 4. But the other thing about vectorization is it's an abstraction that actually, for me, it allows me to think more algebraically. So it's a win-win scenario. We're still sticking in a very productive language, but and we've sorry, I'm scratching on my beard. So yeah, but basically the vectorization for us is and Numpy is really very important to the whole Python stack. Quickly mention Pandas. Pandas basically sits on top of Numpy, and it's really allows you to deal with tabular data structures. It brings in the best parts of R, specifically the data frame. It's very fast. A lot of it's written in C. A lot of it's written in Python, which is like a DSL for compiling out Python into like type Python. It's cognitively simple for general programmers, and munging as a word. Like for people working with data, they think, well, let me just do an experiment. I'll work out clusters of stuff by doing k-means analysis, and I've got the data, and I've got this k-means function, so that's going to be super simple. And 3 weeks later, you're still trying to get the data into the right shape. There's all sorts of outliers. Pandas makes that awesome. So we love the data frame abstraction. You work with data like that. You get to treat either the table as a variable or the columns as a variable, and you can treat them algebraically as well. And data frames are spreading. They started in S as a white paper, went to R, into Pandas, into Julia, and Spark just started supporting them a month or 2 ago. So yeah, just the important thing, I just have to emphasize how difficult this is to dislodge. It's a big towering thing of dependencies. So the challenge for us was we realized we know what we want to do, but we have this problem. We have a large Ruby product. We have a lot of Ruby programmers. Some of them are really just consulting and building on top of the APIs which our product uses. We really wanted to put Ruby on top of all of that stuff, which sounded crazy. I actually tried to rewrite all of this whole stack in Ruby. No, I failed. So, which led me to this crazy idea. But we wanted the flexibility of Pandas. We wanted the speed of Numpy. We wanted to put that in a Ruby API. And we needed to scale horizontally as well because we started dealing with data sets that were up to 40 gigabytes. And we needed to compute everything by everything. So it was 40 gigabytes kind of squared computation. So it was pretty horrible. And yeah, so we had a solution, and that's cool. Thanks. I should probably show you something. So I got demo. You've seen that before. Okay, that doesn't help. Just hang on a second. Okay, so we're also using. This isn't helping. I'm going. We're using. Sorry, I'm struggling to find my mouse cursor. It's all. Okay. I can see it. Okay, so we're using a version of the IPython stuff which is customized for Ruby and customized for our app. I'm going to show you a quick demo of this stuff in action. Let me just increase that. That's probably all right. That's okay. So this is based on a real-life problem that we had, which was we had some crufty old JavaScript sitting around, and it was starting to cause problems, and we want to know, can we get rid of it? So I couldn't find anywhere in Google Analytics that could just tell me just that answer. It could tell me all the browsers and combinations, make pivot tables, but I just thought, okay, we've got this program, let's use it. So just to give you a quick, I'm not going to go into detail, we'll go into that in a second demo, but we load the data, we extract the browser version, we get the total number of sessions that we've had. This is the most interesting part, which is building up a predicate to work out what's modern and what's not. And then some of the Lispy people might already be able to see what's going on here, maybe not. And we get our result, and I'm going to run that, and nothing happens, and there's a reason for that. It's because, sorry, my four-finger swipe is not so good with this finger. It's because we haven't started up the Python side. So we launch that, and then we have our answer, which is 98% modern. So actually, it was awesome, because now we can delete all that old IE crafty code. So how did we do that? So basically, the problem is turning Ruby into data and then turning the data into Python. And the caveat is you could actually turn it into anything if you manage to do this. And you may have heard this from one of your Lisp friends. I certainly got told this a lot, but it ended up being a good thing. So it turned out they were right. S expressions are a universal format for really describing code, and I mean I could be proven wrong here, but you can practically turn anything into any code into an S expression, and it's also extremely simple to communicate over the wire. It is JSON really, and it's very simple to consume as well. So very quickly, the left is Ruby, the right is S expression Ruby. And you guys should all know this anyway, because we're in Poland. And You've seen all this already, so I'm going to just skip straight to that. That's like active record just being rewritten as active Lisp. And that's kind of what we send over the wire. So to reiterate, that's Ruby to S expressions to Python. And it's simple to generate the S expressions. You basically, your methods just have to return an object which you can further compose more S expressions on. And it's quite simple to consume them. It's just a recursive loop. You need to evaluate your operand and your arguments recursively until you hit something primitive like a number or a string. And that's pretty much it. Your one consideration is you either need to get Ruby to create S expressions for a Python implementation, or you use Python to consume S expressions for a Ruby API. And the second version of that is better because it allows you to swap out your implementation. And this is something that I've kept open as an option because Julia is very exciting, and it's cool that the talk's just 2 after mine. Because Julia is really the language where this should, in future, be running on. Limitations and considerations. Is it just like I'm running? Have we just brought data frames into Ruby? Well, mostly, but it hasn't. It's worked really, really well for us. It's been tremendously successful. Our agility has gone through the roof in terms of our main business. The biggest problem I found in a polyglot team is, what the hell do I call that thing? A map, dictionary, hash table. Jose, I see, ended up making a hash dict just to complete the thing. I think dict map is free if anyone's got a new language coming on. So I don't know why, but when you're talking to the guy writing on the Python side, you go, I'll just send you one of these squiggly things. Conditionals. So people want to know, what if I want to have some branching in there? Well, I mean, you don't want to go nuts, but you can do something. And WWLD, what would Lisp do? Lisp would just do cond. So this, after the last 3 days, you should just be able to read this. It's just turning a number into a string based on those 2 conditions and a default. And our stuff looks very similar in Ruby. So the limitation is the actual values that you can use have to be strings or numbers, whereas in Lisp they could be anything. So that's obviously a huge limitation in theory, but in practice it's never actually bitten us. Rocksplot. Let me try that again. Rocksplot. Those things. You can do them. We are able to map over all the columns in a table. We can group things into rows, which usually represent, say, people, like iPhone users and Android users, and we can find out what are the differences between the 2 across every column. We can parallelize that. That's all very cool. So that just works, and to a Ruby person, that kind of looks like Ruby. Until you do that, there's an abstraction leak here, and it's something that's just unavoidable. My consolation is that Spark has the same problem. There's an accumulator variable outside that block, and that's just not going to work because we're crossing the process boundary here. Not only that, the diff variable there is not actually a value. It is essentially a lazy deferred object. So you're not going to be able to add numbers to it. Going back to the lazy stuff, it is this whole example. This is basically that example that I showed you, that was running in the notebook. That does not, after I've run that thing, we still have not hit the Python side yet. That is just building up an S expression. So the whole thing's completely lazy until you need a value out of it. Terms and conditions apply. But otherwise, it's basically turning into that. And I felt I needed to go orange because there's too much blue. But that is that whole thing, basically rewritten. And the last consideration is immutability. It is so important. I think Clojure really influenced me in this regard. I don't do Clojure, but I spectate. And it's pretty much unworkable to have mutation in what would otherwise be a directed acyclic graph. It breaks caching, breaks parallelization. It makes everything much more complicated and makes things slower because you have to defensively copy everything everywhere. Finally, the expressions have benefits that are even go beyond running, like let's say the Python locally, because we can optimize at the API level. If we really think that we're doing a similar thing to a compiler, we're just doing it at an API level, we can actually do things that the compiler can't. We know that certain methods called together can compose into something that's much more efficient. The prime example of this is predicate pushdown, where ultimately you have a large chunk of data that you want to load, and way down the line you actually only end up pulling out 2 columns of that. As long as you don't pass through something like that ends up using everything, then you can push that right down to where you're actually pulling that data out. That's what Spark does as well, but we can do it too. Basically, you need to map one X expression to another X expression, and you can do it both on the Ruby side and on the Python side. Once you have this expression, it's also an acyclic graph computation. You can actually just look at these graphs, and you can see the bits that run down like that, you can do in parallel. The bits that go like that, you can't. We do some of this, but we can do so much more. And finally, as I've mentioned, we can target other things. So I'm going to jump into another demo. For those of you who were like programming in the 90s and were really, really worried about the Microsoft hegemony, this was a sweet moment. So I'm going to load another example. So this is kind of in the theme of PolyConf. I wanted to see something about people using other languages and whether that was changing over time. GitHub has pretty much all data available on a repository. Well, actually, it's Google BigQuery is the best place to get it, because it's obviously enormous. If any of you guys have used Google BigQuery, just paying to use it is almost an impossible task. But I managed eventually. So this is effectively a tiny slice. It's 1 year of pushes in GitHub for 2014 for people who are already using Ruby. So it's kind of biased from my point of view. But we can load that up. And here you've got 644,000 pushes. Well, these are still grouped, but these are unique per language and an account at GitHub. So the first thing you need to do is check for outliers. I didn't do this at first, and then I saw 10,000 pushes in 1 month, and I was feeling quite bad about my own productivity. So I did some investigation, and turns out quite a lot of people use GitHub as a heartbeat monitor. So they commit every minute. And then obviously something else doing a git pull. So they're kind of using GitHub like Redis or something. So it's a bit weird. So we need to detect outliers. So I basically just asked, what's the 95th percentile? That made me feel a bit better. I don't know if I'm at 37 pushes a month, maybe, but it was certainly achievable. And just to reiterate, the notebook is effectively forcing the evaluation of these things. But if I ask for the class, you can see it's actually a scalar, it's deferred. So we can then use this number to construct a predicate, which is basically a vector of Booleans. And we can use that to actually drop down. So we've got down to 610,000 people. So at least 40,000 people abusing GitHub. Well, maybe. I can just show you the wire format of that going over the. This doesn't look like an S expression because any tree can really be rewritten as a series of nodes and edges, and we do that because it ends up being much more efficient, and it allows us to basically we use like Git, we use shards to basically compute whether a node's unique or not, and we don't send up any duplicates. So it's quite a nice way. When we're building up that S expression, we don't know about the duplicates by the time we send it over the wire. It's dropped down in size a huge amount. So that's that. I've already shown you that's what that will look like. And you can see here, you can see there's my less than operator, the quantile operator that's operating on another index. There's my final value, etc., etc. I think it's also, I can also switch to the remote expression because this turns into something else on the Python side. So I'm going to zoom out and do that again. So there's the Ruby. The Ruby turns into Python. The cool thing about that is we've got the times, and we can even get previews. And you actually can't see the preview because this zooming has really caused the tooltip to have a really confused idea of points. But if something goes wrong here, so if I make a mistake with two S's, I can view the remote expression, and you can see the node that failed. And there's a stack trace for that as well, which you can't see. So just to speed forward to the actual number, I'm going to index my data. I'm going to sort it and get the top 10. And I'm not going to dwell on that. I'm going to turn that into a percentage. And we get some unsurprising results. Obviously, 100% Ruby usage because I've restricted it to Ruby users. JavaScript, big. CSS, obvious. Java, probably obvious. Python surprised me, actually. It was nice to know we're not alone. So to switch to that into a time chart, to bring time into the equation, thought I would use the month index. And the one thing that's really cool, we're kind of leveraging Pandas here quite hard. This is what I was talking about, treating things algebraically. We take the top languages over time and divide them by the top languages over time for January. This is just to see relative growth of each language relative to its month of January. So we're getting a percentage growth, and this is incredibly involved. What's actually going on down here? There's alignment happening. This term here is two-dimensional. It has time and it has language. This ends up becoming one-dimensional. There's broadcast, all that stuff. You should look it up. It's cool. I don't have time to really dwell on it. But that's just a table, so I'm just going to forget about that because it's much better if I see this in a chart. So you can see there's a little bit of lag. It's because everything above, I'm reevaluating every single time. Obviously, we don't do that in production. We sort of cache that stuff. This is the chart of that data. I probably should have normalized it to the means, but I didn't really have time. And the one thing that I did find interesting was that you can see that JavaScript is just going up, and C takes a dip, and so does Java, and that corresponds to June, July, and August. So you can work it out. People are not doing that in their spare time. And that's the demo. And yeah, that's pretty much it. We're in London and Cape Town. And thanks very much. It's been inspirational.
Any questions?
Ian.
In production, do you mostly use this in a kind of interactive, exploratory way, or do you have lots of batch things that are using the same plumbing?
It's a good question. No, our primary usage is actually to productionize the stuff so that it gets hit again and again and again. But the notebooks are used for creating that. But I feel if you wanted to do exploration, then tools like R are pretty good, and they're predominantly used precisely for that. But this, for example, I didn't really dwell on it, but we can split this stuff up across clusters. It's very reliable. There's a lot of catering to different shapes of data, and so no, it is mainly meant for repeated use.